Hi, so mechanics students. So this video I'll try to introduce to you the rate of consolidation. Uh, last video I've explained the final settlement of clay. Final settlement. The final settlement of clay, otherwise known as consolidation. Let's try to see this process. So we have a clay layer, and when this clay layer is loaded with a surcharge, water will try to escape the system, either from top and bottom or just from the top. Okay, this process is called consolidation, at which water escapes. Thus, the void ratio is decreasing, and we notice that the clay layer is shrinking. Okay, by a value of STF. STF is the final settlement value, and we define that to be the height of the clay layer times delta E over 1 plus E naught. So H is the height of the clay layer, delta E is the initial void ratio before loading, minus the final void ratio after loading. Okay, so that's how the process is defined, this STF. So basically this is the final settlement of the clay layer after time infinity. Okay, however, most investors, let's say this is a real problem, most investors will be interested to find the settlement of their building or bridge or dam after maybe 2 years or 2 months, so they can prepare themselves for any damage that could be caused. So they specify a certain time. So now we need to talk about time dependent settlement. Okay, and that is dependent on the rate of consolidation. How fast can this clay layer dissipate the water that's inside of it? Okay, so we could define a new one that's called STT, which is the settlement at a certain time, which is less than or equal to STF, final settlement, or it could be defined that STT is a percentage, is a fraction U of STF, fraction of STF. Okay. Now this fraction, which is called the rate of consolidation, okay, is dependent on time. Okay, so we could use this graph right here, U versus TV. So I'm a bit going ahead of myself, but let's just say we know what TV is. Okay, we have TV, we go up the curve and to the vertical, and we get 80%. So the settlement at that certain time will be 80% of the final settlement. So now we go back. What is TV? So TV is defined as C sub V times T over dP squared. Now C sub V is the consolidation factor. Okay, which is meters squared per second. T is the time that we need to find this value at, the settlement at, and dP squared is called the drainage path. So let me get to the drainage path. dP is the drainage path. Actually, let me move to the sides. So that drainage path could be actually one of the two. Could be only one of two cases. Either two-way settlement, two-way drainage, or one-way drainage. Okay, so in two-way drainage, we could imagine that the clay layer, which is impermeable means it can only dissipate water at a very slow rate, and its boundary conditions at the top, we have sand layer, which is very permeable. We all know that water could pass through sand very quickly, so that's permeable, and it could have a very similar sand layer at the bottom as well, again permeable. So this clay layer was loaded, water will tend to go from half point of the center to the top or to the bottom. The rule says if there is a molecule of water that's sitting on the top half, it's not gonna go down. Okay, so it's gonna seep through the top boundary. Same way we could say about the bottom. So really, the longest distance any molecule of water could cross through the clay layer is only half the clay layer height. Half. So I could say this distance, which is called the drainage path, we get this height over 2. So this is two-way drainage. It could drain itself from the top and bottom. What about if you have one-way drainage? We have clay layer, and the top is free, and in the bottom there's impermeable rock. So when this clay layer is loaded, the molecule of water all the way in the bottom must go all the way to the top. Okay, so the longest distance molecule of water could cross inside this clay layer in one-way drainage is height, dp equal to full height. So in this case, two-way drainage, dp will be height over 2, and one-way drainage, dp will be equal to full height of the clay layer. Okay, so that's TV. So what's about this second chart? Okay, that's what the first chart is the average, because U is variable. So if I have a clay layer, the part of the clay layer that is very close to the boundary where it's dissipating water will drain very fast. That means it will consolidate very fast, while the part that's close to the impermeable part, okay, will actually consolidate much slower than U1. So you could say U1, U2 is slower than U1. Therefore, U1 or U percentage in general is not uniform for the clay layer. it's not uniform. So with this chart, we are finding the average. We are finding the average of U inside the whole clay layer. While in this chart, we are actually accounting for the depth Z. So let's say we've got a point of interest at depth Z. So we're counting different Z's would have different U, which would make sense. Okay. So however, the questions given to you, sometimes they don't specify depth. They say calculate the average settlement. So in this case, you use the chart, this chart. If they say to you calculate the settlement at this depth Z, that means you have to use this chart. This chart is known as isochron. Sorry. Isochron. So how do we read this chart? We have Z over dp, so we can find Z and divide by dp. And each one of these curves is a value of TV. So this is 0.3 TV. So it starts from 0, 0.05, 0.1 all the way to 0.9. So let's say we want to find U, and we have TV finding using the same equation. We have Z over dp maybe half, and we have dp maybe maybe it's 0.3. We go to this curve, then we go down, and we read the value of uz. So that's one way. So this method, you can find TV first, then find U. Actually, we start from the beginning. We need to find STF, so the final settlement, that's number 1. Then to convert this to STT, settlement at a certain time, we need to find TV, then U, using either the average graph. What's wrong with me? Average graph or the isochron graph. Okay. So, but this method bases itself on finding the final settlement first, right? But there's another method. So let's say I could find directly STT. So if we go back to the method of finding STF, let's define STF again. So STF is H times delta E over 1 plus E naught. Delta E. So if the clay is normally consolidated, we must say that delta E equal CR log sigma dash PC. This is from my previous videos. Sigma dash node plus CC log sigma dash final over sigma dash node. Sigma dash PC. That's how we find delta E. However, if I'm after STT, I'm after STT. At STT, which is settlement at a certain time, we don't reach STF. Sorry, we don't reach sigma dash final. Actually, the stress in soil now is at STT, sigma dash TT. Okay, so now I can substitute this equation and say instead of sigma dash final, I say sigma dash TT. Okay, the same equation. So the question becomes, what's sigma dash TT? What's the sigma dash TT? Well, here is the core of this chapter, so I hope you can pay extra attention now. Let me just move. Okay. So let's say now when we apply the load on the clay layer, it's the top of the clay layer, and we apply the load, surcharge. The moment we apply the load, we call this T0, the exact immediate moment when we apply this load. Okay? And long term, after we apply the load, we call this TF. TF, which is at infinity. Previously, we had no knowing of T0. We used to define two stages before loading and after loading. We used to find sigma dash initial, and here we used to find sigma dash final, which is most likely sigma dash initial plus surcharge. Okay, that was the previous case. However, now after loading, we broke this down into time equal to 0 and time equal to infinity. So why this distinction? At time equal to 0, to explain this, we need to talk about this experiment. Let's say we have a tank. Okay. So let's say we have this tank here. Inside there's water and there is a spring. So this spring, we call it this spring. This spring is supposed to model the soil skeleton. Soil skeleton. And the water is just a pour water pressure inside the soil. Then we seal the tank with a lead, and it's waterproof, so water cannot seep out of it. And then we applied some loading. Okay. If the tank is too strong, the water is non-compressible fluid, so this spring will not move down. Okay, because the water is not gonna go anywhere. Correct. So we could say the force in the spring is equal to 0 when the tank is full. Okay, so if I attach to this tank a tap, okay, and then I let water drip out of this tank very slowly, what happens is as water is going out, we can notice that the cover is also moving down, and that the spring is compressing. Okay, so we notice that when the tank is partially full, the spring has force, which is a factor of F star. Okay, when the tank is partially full. Now this analogy could be applied to soil. So we can see here that initially the full force is taken by the water. So let's say the force in the water equal to F. Here the force in the water when the tank is partially full equal to 1 minus U times F star. Okay, same thing with this with the soil. So when the soil is loaded, there's water inside, right? At time equal to 0, water did not yet dissipate. Water is still there, present. Okay, so the soil skeleton cannot be compressed, so the soil skeleton does not see any force at all. So we could say that sigma dash naught, which is the effective stress in soil, remains the same. Okay, remains or sigma dash V remains sigma dash naught. There's no addition. It's still as it was before we added the load Q. However, at time equal to infinity, sigma dash V equal to sigma dash naught plus Q. Okay, so at time equal to infinity, what happens? The water dissipates. The water dissipates, just like the spring. The soil skeleton starts to see some force, and this surcharge starts to transmit into the soil. Therefore, we can see that the stress in soil has surcharge in it. Okay, so at time 0, the surcharge has to go somewhere, right? So it goes into the water. So we call this a new water pressure. It's called excess per water pressure. This is the excess per water pressure. Okay, so at time 0, UXS 0 has to be equal to the surcharge, Q, correct? And sigma dash P equal to sigma dash naught. Soil does not get any force, but the water gets all the force. As time passes, we could draw a chart like this. Okay, in red I have my excess per water pressure. Here is time. Initially, as we loaded at time 0, the excess per water pressure gets all the value. This value equal to Q, surcharge. As time passes, it dissipates because water is dissipating. It tends to 0. In blue, so in purple, we have the stress in soil. Initially, it takes 0 from the surcharge and gradually starts to pick up. Okay, until it's equal to Q. Or maybe this is the difference in stress in soil. Okay, so this is defined as the excess per water pressure. So I could say that my total per water pressure is equal to excess per water pressure plus the steady state, USS. What is the steady state? Is what we used to use before, to be gamma water times Z water. So the height of water of my point of interest times the gamma water, which is 9.8. Okay, so so here I want to make a comparison between total stress, pore water pressure, and the effective stresses in soil at time equal to 0 and time equal to infinity after we load the soil. So at time equal to 0, the total stress will be sum of gamma soil times Z of soil layers plus surcharge. And at time equal to infinity, again is equal to sum of gamma soil times height of soil layers plus the surcharge. So that's essentially the same. The pore water pressure, we can find it now to be USS plus UXS. Both cases, USS plus UXS. Now UXS is dependent on time. Okay, so at time equal to 0, USS is equal to Q, like we've defined before, right? So I could say my UXS equal to Q at time equal to 0. So that would be USS plus Q. USS defined as gamma water times Z water, now plus Q. Here, at time, when time tends to infinity, UXS tends to 0 as well. So my U equal to USS equal to gamma vara times z vara, which is what we used to up to this point. My effective stresses, let's say at time equal to infinity, is going to be sigma total minus per water pressure equal to the sum of gamma I zi plus q minus gamma vara times z vara. So we notice that q is present in my effective stresses, while at time equal to 0 it's the same. The rules of solid mechanics do not change for no reason. So I have sum of gamma I zi plus q minus gamma vara z vara plus q. So plus q minus q, they vanish. So it's going to be sum of gamma I zi minus gamma vara z vara, which is the same as sigma dash initial before loading. So you can notice that the soil does not feel the load yet the moment we apply the load. It takes time to feel the load because initially all the load is being taken by the water, as we can see presently in the UXS. So now that we know the UXS is time dependent, how is it time dependent? What's the relationship? Okay, we could define now the rate of consolidation U percentage to be equal 1, which is 100%, minus UXS at a certain time over UXS at time equal to 0. Okay, so at UXSS, so UXS at time equal to 0, that's equal to the surcharge, and UXS at time equal to infinity equal to 0. So let's try it out. At time equal to 0, UXSS, they're both the same, both as 0. So it's going to be 1, so it's going to be 1 minus 1. The consolidation equal to 0, correct? U percentage equal to 0. At time equal to infinity, this tends to 0, so it's going to be 1 minus 0. So the rate of consolidation equal to 100%. Equal to 1. So the formula makes sense now. So in this case, we don't have to use the chart to find U percentage. But it's not that simple because this equation has two unknowns. That's the first unknown, and that's the second unknown. So most likely whenever we want to find the excess pore water pressure, we need to find U percentage first. Again, as a recap, how to find U percentage? We must find TV first, which is CV T over dP squared. Then we plug TV into one of these two curves, either the average curve or to the isochron curve. Okay, and thus you can find UXS at time t. So once you find UXS at time t, okay, we can find also sigma dash VT. So sigma dash T is the same as sigma total minus U, or sigma total minus USS minus UXS at time t. So we could find this using the past chapters, while UXS, which is the excess pore water pressure at time t, can only be found using this process. Sorry. This process right here. So we can find TV, then find U percentage, then find UXS at time t. Now just to recap the sheer amount of information we had to find the rate of settlement or the settlement at time t. We have two methods. So method 1, so we have to find STF first, final settlement. Then we must find TV equal CVT over dP squared. Then we must find U percentage using the average graph or the isochron. then simply we could say that settlement at time t equal u percentage times final settlement. Method 1. Method 2, okay, we need to find STT directly, so we must find sigma total, then we must find as initial, then we must find sigma dash initial before loading, then we must find after that, well, these two they are the same step that we need to do to find STF anyhow. Then we must find TV, then U percentage, then we must calculate UXS at time t, which is 1 minus U percentage times UXS at time 0. Then we could say sigma dash t equal sigma total minus USS minus UXS that we just found here. Then delta E, it depends if the soil is normally consolidated or over consolidated, of course, but let's just use the general case. CR log sigma dash PC or sigma dash node plus CC log sigma dash T over sigma dash PC. Then finally my settlement at time T will be H times delta E over 1 plus E naught. Okay, that's it. Thank you for watching. I hope you got what you need. Thank you.